Okay, let's continue our discussion on universal functions a bit more. Actually, in the last video, I asked you a question. What will be the shape of B if really this A is this five-dimensional array? A is this five-dimensional array. What will be the shape of B if I just apply the sum function with this x is equals to 3? Well, the answer is this is x is 0, this is x is 1, this is x is 2, this is x is 3, and this is x is 4. So once we apply the aggregate or sum on x is 3, this dimension will vanish, and the result will be 5 into 4 into 2 by 5. So the shape of B should be 5, 4, 2, 5. Let's see. So that's the shape. You might be wondering what will happen if we just call the sum function without actually any input argument, any access specification. In that case, you will be having sum of all the entries in the array B, all the entries in all the x's. This particular thing might be achievable by, for example, sum in, let's say, x is 0. That means this 5 is just gone. Now the result is 4, 2, and 5. Now if we call the sum on the result, which is just, the result is just 4, 2, and 5, and then we call x is equals 0, that means this 4 is also gone, and now the resultant array is 2 by 5. If we now call the sum on with x is equals 0, this 2 is also gone, and now the result is just 1 by 5. And now we can call the sum function without any access argument, because now the array is one-dimensional, and the result is again the sum of all the entries that you have just seen earlier here. So it is important to play with the dimensions and access and all that stuff, because when we are working with large data files, it becomes really handy to be fluent in the dimensions and axes and all these universal functions, because being fluent in all these, most of these universal functions, and being able to work with dimensions more comfortably, working with axes more comfortably, will give you really will give you a speed up in your programming and achievement in your tasks as well. Next, we talk about some trigonometric functions. I've not talked about all arithmetic functions. I've just shown you a few. There are so many of them. Let's talk some trigonometric functions and comparison functions as well. Just to give you a flavor of what these kind of functions are, I will just explain a few of those. So let's say A is again np.random.rand, let's say, and let's say I have this as 5. So this is an array of 5 elements. So what next I do is I call np.sign, for example, on A, and that will apply the sign function on every element of A, and the result will be returned. The same can be achieved again by calling A dot, for example, A dot, let's say if there is a sign function, because there was a add function, so we might be hoping that there is a sign function as well, like the sum function. So is this there? The answer is no. I mean, not all the functions, not all the universal functions that are called by NP, they have their equivalent object methods. Remember this NP dot functions and this object dot functions, they're not equivalent in each and every kind of. So you might be wondering, for example, if A dot sum is there, so you might be wondering that A dot sign might be there also. Remember, A dot sum is a sum of all elements on A. If you say A dot sign, that means what? I mean, np dot sign, and then you give an array A makes sense, because now you have to apply the sign function on every element of A. But when we call A dot sum, it was not the sum of every element of A. I mean, that doesn't make any sense. So remember, I mean, although there are a lot of universal functions in NumPy, don't try to pretend that each and every NumPy function that is called by np dot has an object equivalent as a dot or array dot, something like so, and like so. So that's sine function. We can have cos function. We can have several other trigonometric functions. I mean, there are a whole plenty of them. They are available. Hyperbolic functions, sine hyperbolic, cos hyperbolic, sine inverse, for example, np dot arc sine, that is available. That is element-wise sine inverse of a. Similarly, we have degree to radian function, radian to degree function, and all these kind of trigonometric functions as well. Next, we dive into comparison operators. Let's say, for example, we have A as np dot random dot rand. Let's say 5 elements. Let's say B is np dot random dot rand. That's again 5 elements. And let's say we call np dot, let's say, greater AB. The result will be a Boolean array. Let's say the result is R. That's a Boolean array. And if you see this R, it will be false where this condition is, if A is greater than B element wise. Wherever this is true, the result is true, and otherwise the result is false. So if you see, for example, the values in A, if you see those, if you see the values in B, so you can see now the only the first, so A is greater than B, that is false just for the first entry, because this value is not greater than this. For all the rest of the entries, the first values, they are larger than their corresponding values in B. Yeah. So, but you may, I mean, you may be applying an operator and just you're good to go. For example, result is A is bigger than B, and that's exactly the same thing. If you see this R, so whether you're using comparison universal function or you're going to use an operator, that is perfectly okay. Similarly, there is a greater than or equal to, greater than underscore equal function. There is a less function. There's a less underscore equal function, not underscore equal function, equal function, and their corresponding uh, operators are also there. So sometimes working with operators is much more handy, although the efficiency is exactly the same. Next, we talk about some logical operations on arrays, particularly Boolean arrays. Let's say we have A equals np dot random dot rand, and let's say we have 10 elements. That's our array. And what we do is we generate R1. The result 1 is simply the A is, let's say, less than 0.5. Let's say that's our R1. And R2 is simply the complement of R1. Let's say that's the R2 is that. So next we see, for example, R1 is this, and R2 is exactly the complement of that. Yeah. So false, 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 that means true, 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 false. I mean, this operator just applies the complement or not. We can do the same. We can achieve the same stuff as writing, for example, R2 equals np dot logical not on R1, and that will give us this exactly the same result that we have just achieved. Okay. So next, for example, we have let's say A equals np dot random dot rand. Let's say we have 20 values, and what we do is we say, okay, we pick all the values that are, so let's say B is A, so B is an array. Let's say B is an array, or IDX is an array, that all the value pick, I mean, if the value is greater than, as long as the value is greater than 0.2 and the value is smaller than 0.8, just pick all these. So it will go element wise and see, it will apply the first condition and generate a Boolean array. Then for this particular condition, you'll be having another Boolean array, and this operator will take the AND, logical AND of the Boolean arrays, and you'll get a Boolean array as a result. This thing. The same thing can be achieved, for example, by applying the np dot logical underscore and function. So there are functions and there are operators, their equivalent operators. They're also there. One more thing that I really need to specify that is mentioned in the slides as well, the missing values or the NaN values or the functions that are NaN safe. I really should mention those as well. Just to wrap up things quickly. Sometimes it is possible, for example, let's say a equals np dot random dot brand, let's say, and let's say we have 5 entries, okay? And what we really do is we just have a at index 3, we just place np.nan. So what happens really is if you see a, it has all the entries, for example, the very first entry, the second entry, the third entry, but this particular entry is nan. What the problem is if you now call the sum function, for example, on a, you will get nan. And the reason is just one nan entry actually produces the whole calculations to a nan. And that will be a problem also in data frames and in data sets that we'll be working with. These missing values will be there, and normally they will be reported as NaN values. And if you do not care about NaN values, you may be getting results that are really unexpected. So one possibility is to just locate these NaN values and just get rid of those, or just ignore them. Another kind of way is to use NaN safe functions, for example, NaN sum a. If you see that, that function basically produces the summation of all the values by ignoring all the NaN entries, all the entries that are NaN. So yeah, so and like NaN sum, there is a NaN multiply, there is a NaN product, and I mean there are a lot of functions that are NaN safe functions. Whenever you think that your data may contain missing values, and you're thinking that just ignoring the missing values and doing the calculation on the rest of the data is perfect for you for a particular scenario, use these NaN safe functions. There are so many of them that are available. Yeah. So one more thing, if I call, for example, a dot is sorry, np dot is nan, and I call that function on a, the result will be a Boolean array where wherever there is a nan, that will be a true value, and the rest of the values will be false. So yeah, so that's basically it. So you can locate where the NaN values are. You can locate them like so. Let me just introduce some more functions, some more important functions. Let's say we have a equals 10 asterisk np dot random dot rand, let's say 5, and let's say these are the values. If you see, these are the values. Maybe I can just maybe I just want to just get rid of these decimal positions by just calling a floor function. So NumPy has a couple of functions, basically more than a couple of functions, just to deal with these floating points. If you want to truncate the missing value, if you want to truncate, if you, for example, want to this floor means just delete the decimal portion. If you call, for example, np.ceil, ceil, I guess, if you call that, you will get all the values truncated, but then the remaining result is incremented by 1. There is a round value, there is a round function, there is a truncate function, there is a fix function to handle these floating point of values, to rounding off these floating point of values in NumPy. And there is a lot more. There's a lot more. I'm just finishing this basically 5th point here, the rounding floating points here. And in the next video, we'll be talking about our output arguments that can be set in NumPy universal functions. Because you might be thinking, when there are a lot of operators available, why one might be using these universal functions? Well, one answer is that's another way of doing the same stuff. But there is another cool answer that I'll be answering. That is a part of kind of features of universal functions. So hope to see you in the next video.
Welcome back, guys. So here's another quiz for you. Create an array myArray1 using numpy.random.rand for 50 values multiplying by 10. So it's the same way that Kashif has done by multiplying it by 10 if you see the video. So create an array like this, that is myArray1, and then remove decimal point values of myArray1. Kashif has introduced a function for that. Try that, and then make another array that is myArray2, and store only numbers that are greater than 5 from myArray1. Right? So this is simple, and we've done such things before. So by the end, now till here you'll have two arrays, myArray1 and myArray2. And now we want to sort myArray2 in ascending order, and we want to sort myArray1 in descending order. So how can we do that? There can be multiple ways of doing that. Try it, and then we'll discuss it in the next video. You can try it on your own, and maybe it can happen that my solution is different than yours, like in maybe a minor way. But that's totally okay. Our purpose here is just to learn. So I'll see you guys in the next video. Hello, people. So you guys were given this task, so let's just quickly solve it together. Jupyter notebook, and okay. So first of all, let's create an array, and we want to create it 50 values, and the task was to multiply it by 10. So this will give us, oops, module object not callable. 1 second, what did I do? Oh, okay. Random dot, there should be a rand here, right? Yeah, so this is how we create an array using np.random.rand. And so the next task was to remove the decimal values, right? All the decimals. So how can we do that? So we were introduced to floor, right? So if we do this, this should remove all the decimal values, right? So now we have 5 1 5 5 and all. So that's a solution to our task. And then we were asked to, right, we were supposed to make let's just read out the task. So make another array, myArray2. Okay, so I didn't name myArray1, I just used A, so I'll just use B as myArray2, and store only the numbers that are greater than 5 from myArray1, which is A, right? So let's do that. Let's say B equals A, and from A, what do we need? We need all the values of A that are greater than 5, right? So yeah, this should, yeah, so we have 9 6 9 6 7 8 9 and 6. All the values that are greater than 5 are here. Okay, all right, cool. So next, we're supposed to sort B in ascending order, and we have to sort A in descending order. Okay, so that should be simple. First, let's do it for B. For B, we can just use B dot sort. There's a function of sort, right? It sorts all the values in ascending order. There we go. B is sorted in ascending order 6, 7, 8, 9, right? And A, for A, there can be more ways, but I'm just going to do it like this. A dot sort, that will sort A in ascending order, right? But we want it in descending order. So how about I do this, something like this? Do you guys recall this? Start, end, and -1. Do you guys remember this? Yeah, that will basically reverse the whole array, which is in ascending order, so which would automatically make it in descending order. And there we go, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So yeah, A is in descending order, B is sorted in ascending order. B contains all the elements of A that are greater than 5. A contains no decimal values. Floor was for this purpose. So yeah, all tasks achieved. Good, cool. So I'll see you guys in the next video. Thank you, everyone.
Welcome back. In this particular video, we are going to discuss basically the output arguments, one of the features in the universal functions of NumPy. Primarily, I'll be answering the question, or will be trying to remove or solve the confusion that if an operator is available to achieve the universal function, should we really go for a universal function call or not? Well, in certain cases, I would say yes, and I'll be explaining this just with this particular example just once. Let me first tell you a feature of these universal functions. Let's say we have this let's say np dot range, let's say 5. And let's say we have this y as just np dot zeros, and let's say these are also 5. And what we'd really do is np dot np dot sum, np dot sum. What we really do is we basically or np dot, let's say add, and we really add a value 10 to every value in a, and what we do is we store the result in y. So if you do that, the result basically is in y, and now if you see y, that is basically this. Yeah. So you might be thinking this is doable just by doing the following thing: y equals np dot add a10. That's one way of doing that. Another way of doing that is just say, okay, a plus 10. What is so fancy about this? So the same things. I mean, whether you set an output argument like this, or even if you do not specify the output argument right away, you can do that. Then I would say, okay, see, for example, another example where A is the same array, A is the same kind of array, and your output is simply np dot, let's say zeros, let's say 10 values. And what you really do is you do, okay, np dot sum a 10, but you place that in y every other entry. So every other entry. So starting from the very first index, you skip every other entry and you do that in z basically. Yeah. So yeah, oh, what's the problem here? Axis 10 is out of the mount. Oh, what I've done? Oh, sum. I should add. I should call add. That's the problem. Yeah. So that's the result. I mean, the result is saved at appropriate positions that I specify in there in an array, and the rest of the values are 0 as initialized. When, well, one could say that I can do the same stuff using this particular command. So what is so fancy again? I can do this, for example, a plus 10, or a plus, for example, 50 maybe, whatever the a is, and the result is exactly what I was expecting using this out. Well, the answer of using this output argument is not really that whether you can do that otherwise or not. The implementation of these universal functions and actually the vectorized implementations and the compile level implementations sometimes makes this efficient to use this out parameter inside the universal function rather than to explicitly assign that after the calculation. And the reason is, as they say, the reason is basically working on small kind of arrays, this might be negligible whether you specify an output argument inside the universal function or not. But working with very large arrays, very large kind of arrays having a lot of values, these if you assign these values explicitly, it actually requires the storage of some temporary result inside the memory, and then at a subsequent step, maybe that temporary result is copied into this output variable. However, the implementation of NumPy ensures that if you specify basically this out argument inside this universal function, by not using, for example, an operator, by calling actually the universal function and specifying this output argument, it basically ensures the storage. It basically ensures that there will be no, practically there will be no temporary storage, and all the result that will be stored directly into this memory location, thereby saving a lot of time while working on very, very large arrays. So it sometimes become handy to use universal functions if you're working with large kind of arrays to gain a bit of efficiency as compared to the operators, especially for large arrays, to avoid the temporary storage and the overhead of temporary storage. So yeah, so that's about the universal functions. There's a you should see the documentations of this NumPy universal function. There are a lot of them, and you should be using a lot of them. Later, we will see an example of k nearest neighbor. We will implement k nearest neighbor from scratch in NumPy, where you might be using the indexing and some of the universal functions in action on real data. But you should go through all these functions, and you should know which function is doing what. So I end this video here. In the next video, I'll be talking about image data. I mean, what if we want to manipulate images? Well, you might be thinking, what has NumPy to do with image? Hold on for the next video. Wait for the next video. I will show you what NumPy can do with images. So hope to see you in the next video. Okay, let's play with images using this NumPy. Image data basically, or images, they are arrays, sometimes multidimensional arrays. If you think, for example, about RGB images, then each image is basically, each image consists of a red band, a green band, and a blue band. So basically, this basically a three-dimensional array, an image, where the number of pixels, the number of rows, and the number of columns, they basically represent the number of pixels of one band. And then we have red, green, and blue band, the channels, sometimes called the channels, they are available for one image. So you may, for example, have an image with 200 rows or 2000 rows, maybe 141 0 columns and 3 channels. That means this basically array is of this is basically one channel. This is the size of one channel, and you have 3 channels of those. Well, if you see one particular channel, it's a two-dimensional array of numbers. Each number is between, if that's an 8-bit array, each number is between 0 and 255. And that, for example, if the image is alone, that is considered to be a grayscale image. If you have RGB image, then for each location, for example, if this location, for example, this particular location is IJ location. So that for this location, you might have 3 numbers, one number from red channel, let's say 200, another number from green channel, let's say 100, and another number from, let's say, blue channel. Here we mean that the more red contribution, a little less green contribution, and the blue contribution is very small. And this particular, I mean, we should call this as a tuple. This particular tuple, 200 and 115, that basically represent a particular real life color that is displayed there on the images. So basically, each location consists of 3 numbers, R value, green value, and blue value. And that's why this RGB image looks like so. So let's read and manipulate some of these. Let's play with images using this NumPy. Basically, when we read the image, we will read the image using a matplotlib library, although there are other image processing libraries like Pill, Python image processing library, sometimes called Pillow. There are other open CVs there. I mean, you can do a lot of stuff there. There are a lot of libraries, but just to show you basically the how can we manipulate images using NumPy, I'm going to just import another library called matplotlib that we will see in detail later in this course in the visualization sections. But right now, I'm just using that for basically reading and writing and showing an image. So let's say import matplotlib.pyplot. Don't worry, we will see this matplotlib in detail in our later in this course in the visualizations when we'll start graphics and visualizations and all that stuff. So right now I'm just importing this library just for image reading and writing and showing. So import matplotlib.pyplot as maybe plt, import that. So that is imported. Next, what we really do is we read an image. The image is located somewhere. Yeah, I have just an image of a particular bird, an RGB image here. Let's save the path of this image and just go back to Jupyter. And okay, im is plt.imread, and we have this raw, and that the image is basically there. That's the image in the variable m. I want to show you the type of this m. What is the type of this m? That's basically the NumPy array. It's a NumPy array. Let's see it's because the images are arrays of numbers. Each image, once it is available to you in form of a NumPy array, you can apply all the NumPy knowledge you have, and you can play with this array basically, and then you can write that array again as an image, and the image is manipulated if you want. So for example, let's see the shape of this image or this array. Right now this image has this particular shape. Yeah, so it has these many rows, these many columns, and 4 channels. Why 4 channels? It should have just 3 channels. Let me plot that image, plt.mshow this m, and see what happens. Yeah, this one. I'm not sure where is this 4th channel comes from. For example, if we create a new image, let's say m3, and we create image, just we get all the rows, all the columns, and we get everything till the 3rd channel, and that will be m3. That should also be the same image. Why not? What's the 4th channel is doing there? So plt.mshow, for example, m3, that is what? That's the same thing. So there is some 4th channel, just maybe for alpha or some color manipulations, but we will be dealing with this m3. Just I've picked the first 3 channels. Shape, that's there. Yeah, so this is there. Now let me display, for example, this image, the red, green, and blue channels, all of them. So let me first display the red channel, and blue channel, and then green channel. Or why not we display this image with all different channels? Remember, the red channel is basically m3. Let me call this m3 simply as my image. img is m3, just to get rid of this m3. So that is image. So my red channel is basically image 0. That's my red channel. If you now see this r.shape, you will get this particular thing. And by the way, you can play with this red channel, you can play with this green channel. Let me first show you all the channels individually, and then we will change the colors, and we will do some stuff with this. And all these changings of colors and manipulating this image will just happening with like we're doing, for example, we will be just playing with an array, and actually everything is happening with an image. So let's just plot all these individually. So figure AX is equal to PLT dot subplots. Don't worry if you don't know what subplot is. Just think about it's an array of plots and the array is 1 by 3. So that's array of plots. Just for now, that's okay. Later on, we will be dealing with that in detail when we'll be studying Matplotlib, Seaborn, Bookie, and stuff like so. So maybe a red channel, a green channel, and maybe a blue channel. Yeah, so blue channel, these are my channels. So what I do is for AXI in enumerate ax.flat. So what I really do is I set axi.mshow m2 or image, basically image. Which channel of the image? Well, the ith channel, whatever the I is, and I set the color map as gray. Okay, so then what I do basically is I set the x ticks and y ticks just to get rid of these axis numbers around the image. I just get rid of those, and then what I can do is I can set, let's say, dot set, let's say, x label as let's say channels I dot that's my x label, for example. What should be the color of that? So let's set the color as whatever the channel is. So channel I dot lower, because this R is upper, this G is upper, so let's make them lower and do that stuff. Let's run this code and see what happens. Oh, invalid syntax. That's what happens. Okay, I guess, yeah. So that's a red channel, that's a green channel, that's a blue channel, as you're seeing here. We can actually modify the figure by just setting different sizes. So maybe we set a size in inches. Maybe that size is, let's have 20 by 50. Let's say that's the size. What happens? Let's see. That might be a huge size. But yeah, so that's red channel, that's a green channel, and that's a blue channel. You can see the red is more, the red channel is more, brighter, and the green is a little less brighter, and the blue is less. That basically means in the image, the red content overall is more than blue, more than green, and the blue content is really small. And that's what is there. Now, let me, for example, increase the red content in the image just by doing the following stuff. What I really do is I just pick the image, and I pick the image, and let me take the copy of the image. I am image2 as image.copy. Let me just take the copy just to not disturb the original image. And image 2, what I really do is I pick the red content, or I pick the blue content basically, which is index at 2, 0, 1, and 2. That's the blue content. And I just increase the blue content. And then now you will see the blue content is, oh, it's roughly the same again. Why not? Why it's the same? Oh, because I'm showing the image and not image 2. So let's see. Now, yeah, so that just creates all the colors actually the same, and yeah, that's a bad thing. Let me create this as image 2 multiplied by, let's scale the color by, let's double the color, and let's see what happens. Yeah, so doubling the color gives this. Let's scale the color 10 times, and we're not seeing any success here. Why don't we actually do this? So image 2, 2, let's increase that color very high, and then just display image2, plt.imshow image2. What we are expecting is more blue content in the image. Rather, yeah, it's bluish now. Oh my God, because we have increased the blue content. Clipping input data to a valid range of imshow RGB data to 0 and 1 to floats 0 to 255 and teachers fine. Whatever the data was, it clipped if it goes beyond the boundaries. See that? If we, for example, if we select a particular, so let's have image again. Image2 is image.copy. Let's have again image2. And what if we just pick a particular block starting from, let's say, index 100, or maybe starting from index, let's say 400 to, let's say 500, columns 400 to 500, and we just focused on, let's say, red color, or maybe green color, maybe green, and we just increase that green color a little higher. Then what we'll be looking at this particular box or bounding box will contain more greenish effect than the rest of the area. So let's see, plt dot image 2, plt dot imshow image 2. Let's see that what happens. Yeah, are you seeing this? Are you seeing this block? Let me make this block a little wider, just to show you. Let's have this to 1,000. Why not? Let's set this to 1,000, and now you can see the impact more. Yeah, so you can see that impact much more. If, for example, what I really do is I also reduce the colors of the rest of the channels to 0 and just produce the color of this green one. What I really do is I go to channel red and I say, okay, lose your contribution in this block. And I also go to channel 2, the blue channel, and I ask, okay, lose your contribution. And I make the contribution of this green really high. Then what you will be seeing now is a solid green block. You will not be having a see-through there, like you're seeing now, kind of alpha blending kind of thing. You will not be seeing that because the contribution of red is 0, the contribution of blue is 0, and you'll be having now all the green, solid green there. Yeah, so that's solid green. There's no see-through inside. Yeah, and now we can save this image using plt.imageSave function and stuff like so. But the purpose here is to show you that all what you're doing is basically you are just playing with the NumPy array, and the actual things are happening with the image. Let me just flip the image. Let me flip the image from left to right. Let me just flip it. So what I will do is I will do the following. Let me flip the image horizontally so that you can see the image completely flipped horizontally. So let me first have image 2 again as image.copy. So let me then plt.image plt.imshow image 2. That's our original image, if you can see. Now I'm going to flip it horizontally. So what should I do? First of all, I will see, okay, I will generate index. Let's say the index is np.range. These are all the index of the columns. So how many are these? Image2 dot shape. Which shape? The shape of the columns, basically the column index is 1. So these are my indices. So indices are all generated. Okay. So what I do next is I sort the indices in the reverse order. So I generate, let's say, image 3, or maybe I just call I generate another image 3, as image 2 with all the rows as it is. The indices, they just get sorted in reverse order. which means the last index becomes the first index, and the first, I mean, they just sorted in reverse order, which means the last column should appear in the beginning, the second last should be appear as a second column, and so on. So that's my image 3. I'm just playing with an array and see the effect now. Plt dot mshow image 3. And let me show you the image. Oh, it's the flipped variant. It's the horizontal flipped variant of the original image. Can you see that? You can flip that vertically as well. So should I write the vertical flip as well for you? Should I write the one-liner for that? Yeah, let me write the one-liner for a vertical flip. Yeah, so let's do that. So image 3, plt.image3. Again, don't disturb this, don't disturb this, vertically flip this. So how can I do that? So np.arrange, that's one liner. I hope it works. np.arrange image3 dot shape of 0, whatever that is, that's the index, and then I want this index to get reversed, and whatever the result is, I want to show that. So, oh my god, it works. That's one liner for that. That's amazing. You see, I mean, I'm playing with indices in NumPy, and I'm achieving effects that are beautiful. I mean, I can do much more with images, with videos, with text, with audio, and all that stuff. And that's why you should be noticing. That's why I mean, having a knowledge of NumPy is essential for any data science package, because all the data science packages, they all built on NumPy. If you have a good grip on NumPy, indexing, manipulating, playing with the arrays, axes, dimensions, and all that stuff, you'll be very, very fluent in data science. So yeah, I end this example here. In the next video, I'll be coding one more example. I will be showing you more power of NumPy, and we will be implementing k-nearest neighbor classifier from scratch in NumPy. So hope to see you in the next.
So I have another quiz for you guys to help you learn better. So we have started learning how to play with images, right? So here's your task. Import that bird image that Kashif used in this lecture 32. You can get that image from the link that contains all the documents that's given in the start of the course. So you can get that image from there, and take the original image and make a blue box. So we're supposed to make a blue box, right? So with the color value of 200. Making a blue box means that red and green values will be 0, right? So where do we have to make this blue box? We have to make it from, so the x-axis from starting from x-axis 1000 to 2000, and y-axis from 100 to 500. So your grid, in your grid, these values should, there should be a box on these values, right? On the y-axis and x-axis. So try this, code this, and I'll code it for you guys in the next video, the solution video. See you guys then. Okay, so let's solve this quiz. So I've already imported the image. There was it was just an easy task. Plt.imread, imread, and then I just entered R for raw, and the whole path where the image is. So now img contains the image, and plt.show, I just showed the image to you guys. So let me just make img2, and let me just copy, right? I just want to copy the what. Okay, it took a little time. Okay, So it was just taking a bit time to do the process. So I just copied it. Let me just remove this from here. So now we have img2. In img2, so now what was our task again? We had to make a blue box with color value 200. It can be any other value, but it's just specific here, so we're gonna do it with 200. And the x-axis and y-axis are given, so we have to make a box within these axes. So let's do that. How can we do it? We have seen Kashif making a box in the video, so it should be pretty easy. So the values are y-axis are 100 to 500 and x is 1000 to 2000, right? So 100 to 500, we want to start our box from 100 y-axis 100 to 500, and on the x-axis 1000 to 2000, right? These are the values. Yeah, these are the values. Okay, so now let's say the 0, let's say r, we we had to set r to 0, right? Because we only want blue. We just want a blue box. We don't want any participation of the red or green in it. So I'm just going to copy this all. Yeah, so 0, and so that's R. This is G, right? The 0 and first index. Now, here is what we want to play with. 1000 and 2000. So the second index, which is blue, we want the color value to be 200, right? That was what we wanted to do, right? So let's just see if it actually works. I am show and mx2, we want to show this. Okay, let's see if it I have made an error in the syntax. Oh, oops. Okay, that was a syntax error, and have I made it somewhere else as well? What's wrong? Why is it doing? Oh, okay. Okay, it's just a syntax error, nothing to be worried about. Okay. Come on. Another syntax error. Where have I? What's wrong with 100, 500, 0? So it's giving an error over here, but shouldn't. Oh, okay. Maybe this was the problem. Yeah, that was the problem. So now we have a blue box, and we have the on the y-axis it's starting from 100 to 500. On the x-axis it's from 1000 to 2000. Okay, cool. So that was our task, and we've achieved it. Cool. So I'll see you guys in the next video.
Okay, in this video, we are going to talk about a famous classifier in machine learning called k-nearest neighbor classifier. The implementation of this classifier is available in scikit-learn package as well as in other machine learning packages as well. But the goal here in this particular video is to just build that classifier or the basics of that classifier from scratch using NumPy, and basically to show you how much NumPy is powerful in its indexing and all that stuff, and kind of writing certain kind of one-liners to build these kind of complicated tasks just very quickly. So hopefully you have, till now, you have a good grip on NumPy indexing, universal functions, axes and dimensions and all that stuff. So let's dive in and build one example using this NumPy to get a good grip on more about this NumPy and see the usefulness of this NumPy. We'll be working on iris data that is available in data sets, both in scikit-learn as well as in Seaborn and other packages as well. So let's start. The purpose here, just let me show you what a k-nearest neighbor is. Let's say you have this particular object, object 1, this particular object 2, and let's say you have so many objects, let's say n objects. These objects primarily will be represented as arrays of numbers, maybe. So you can think that first object is just one array of some numbers. The second object is an array of numbers. The third object is an array of numbers, and all that. We call these arrays as feature vectors or descriptors. Now, let's say you have another object, let's say object T, which is also represented as an array of numbers. So your goal is to find out the neighbors or the objects that are closest to it. So one way of finding out the neighbors is to just compute the Euclidean distance, because all these are just vectors. So compute the distance of this particular object from all the objects, and then see what is the first neighbor of it. By first neighbor, I mean what is the closest to it. The second neighbor is the second closest to it. The third neighbor is the third closest to it. If, for example, we have set the value k is equal to 5, we can pick the 5 nearest neighbor of this. And we will see, for example, if this is a classification data set, and this has category 1, this has category 1, this has category 2, and maybe someone have category 3 and stuff like so. So we will see among these 5 nearest neighbors which category actually votes the most, which category wins. Whatever the category that wins, whatever if this particular object got the most neighbors from what category, this particular object is assigned that category, and that kind of classification scheme is called k nearest neighbor. So let's build this k nearest neighbor classifier using NumPy from scratch, by using whatever knowledge of indexing and universal functions and axis dimensions, whatever knowledge we have so far. So let's build this one. So let's load, first of all, let's load the iris data. Let's see what the data looks like and stuff and all that stuff. So let me load that data from sklearn dot datasets import load iris. I guess that's correct. Yeah. So iris data is basically load iris, and it will actually give me the iris data. Later on, I will show you basically. Sorry, what is that? Just let me show you the iris data. I mean, this is the data that is being loaded there. Later on, I will show you in pandas how can you load your own CSV files and all that stuff. So this iris basically has a lot of properties. Let me see, iris.data, that's a property. And if we see the shape of iris.data, the shape basically is 150 by 4. Basically, there are 150 objects, each having 4 numbers. So 150 different objects. Further, there are other properties of iris. So let's have this x as iris.data. Let's save that in x. And let's say we have y as their categories. So the targets, so the target, that's our y. So if you see np dot or you see y dot unique, for example, you will see has no object unique. Okay, let me call np dot unique on this y, and we'll be having 3 classes. So this has 3 classes, class 0, class 1, and class 2. So if you see the shape of y, you'll get oh, I'm making a lot of mistakes. If you do the shape of y, if you see the shape of y, that is basically 150. So for example, if I just access element at index 100, the element at index 100 belongs to class 2. So that means the object which is the row at index 100, this particular row, that particular data point, that belongs to class 2. Okay. So first of all, let's build a train and test split. Let's just get some of the data out from this data, and build our classifier. So let's say, for example, let's define our function, define my strain test split. Let's say this is our function that takes x and y and take the test split percentage, test size, maybe test size. Let's say test size, and we really want to return certain the training data and the test data. By the way, those who are interested in this in scikit-learn, there's a train test split function. I'm going to actually write my own implementation for that using NumPy, and I basically I want to show you that this is really easy, not that tough. So yeah. So first of all, let's say let's arrange an index. Let's do a random permutation. So idx is np dot random dot permutation. So of np dot range of y dot size. So that's all the random index that is being generated. Okay. So next, what we see is we pick the test idx as test idx, whatever that idx is. So idx, these are my test idx starting from 0 to floor, basically. So if the test size is 25%, so what is the test size? Static y dot size, that's our total test size. And maybe we want to, let's say, floor that, np dot floor. Maybe we want that number computed outside. So that is the test value. Maybe let's say we have 20% test data. So how to compute that? So that's the size. So t size, test size is that. Okay. So 0 to test size, where the test size is not included. Obviously, the test size is not included. So that's the test size, maybe. And the train index is, for example, the random index starting from test size to end. So here we need not to actually write a 0 there. We just go to test size, and then from test size to end, these are indices. And now the train x, or train x, is simply x train idx and all. That's our training x. The train y is simply or let me call that as x train. X train is this, and y train is simply y with the same kind of credentials. Train idx and x test equals x test idx, and y test basically is y test idx. Yes, and we basically return all these values: x train, x y train, maybe x train, x test, whatever sequence you want, y train, y test. So you return those, and you basically have this function. Maybe you can have smarter implementation than that, but this is basically the equivalent kind of implementation that is available in scikit-learn. So we have this. Let's have now x train, y train, x test, y test. Let's call that by supplying the test size, maybe 20% or whatever. That is, let's say, my train. If there is no error, it should work. X, Y, and the test size is, let's say, 20%. So there's an error. Let's see where is an error. TS. So slice index must be integers or none. So yeah. So I'm not doing basically the slicing here. I should not do the slicing. This is not the slicing. This is like so. So because this is array inside, this is the index array inside the array. So this is no longer a slice. So I should just pick that. That's an array of indices, and that's basically the size I really want. Okay, so then if this is the size, what should happen? Why this is not working? It should work. Should I call here x dot shape 0? It should work. This ds should be a number, and idx is an array. Idx is an array. ds is a number. Maybe we have messed up these things. X dot shape 0. Although y dot size should work, but maybe this thing. Yeah. So I think it should work. So let's run it again and see if the error still is there. The error is there. The error is slice indices must be integers or none, or have an indexed method. What's the problem with that? Let me just do that let me just do that. Let me just print this thing simply in my here. That's the indentation problem. Yeah, that's so now ts test size is not defined. So let's say test size is test size is, let's say, 0.2. Then what's the problem here? I'm not able to locate the problem. This idx is what? So this idx is this thing. It's an array of indices, all the indices, fine. Then what is this thing? What is this ts? What is that thing? This ts is what? It's 30. Oh, it's yeah, I should convert that to integer because that must be an integer. That's the problem. Yeah. And p.float actually returns yeah, that's a problem. It returns basically a floating point number, and I should be converting that. Yeah, everything works now. That's a problem. So np.float, it returns a floating point number, and the array requires basically, yeah, everything else is okay. Just convert the index to be an integer. Yeah, so healthy debugging, fine. Take some time, but oh, there's another error now. What's the error now? Too many indices for an array. Train index, these are too many indices. Yeah, I know that's a problem. This y is no longer a two-dimensional array. Why we are treating that as a two-dimensional array? That's another bug. We just got it. Yeah, everything is fine now. Great. Yeah, great. So now if you see this x train and y train, if you just see the size of x train dot shape, if you just see print that, you will get 120 elements in x train, and simply if you see the y train dot shape, you will get the rest one. So 120. Similarly, x test dot shape, that is 30, and y test dot shape, that is 30. Great. Now we have data that is sometimes called the training data, and we have this data which we will use for testing for our performance of our classifier. So what next? Now what we are going to do is basically we are going to compute the distance, the Euclidean distance of every data point in X test with every data point in X train, because we want to classify these 30 points in X test. We want to classify each of these points based on the best neighbors it can have. Let's specify the value of k later on, but let's first compute all the distances. Let's compute the distances of every test point with every training point. And here you will see the power of NumPy. I'm going to write a one-liner. So fasten your seatbelt. D, that's a distance matrix. np.sum, fine. X, that is my X train, basically. if I'm right, that's xtrain. Yeah, xtrain, that's a variable. Now in xtrain, what I'm going to do is I'm picking everything. I'm adding a dummy dimension here using new axis, and I'm just adding a dimension inside. Okay, so this will become 130 by 1 by 4 matrix. Okay, well, I'm going to do that. Then I will subtract x train x test basically. And what I'm going to do here, I'm subtracting numpy dot new axis and everything else kept as it is. That will actually do a broadcasting for me, and it will subtract, actually it will subtract every test point from every training point, and it will give a matrix that I will show you just so this is basically a difference matrix. Let me just give you a result of this, the difference matrix. Let me give you the shape of that. Oh, the d dot shape is nothing. Why not? Because I've done the sum. Great. Wow. Let me not apply the sum now. Let me, oh, okay, I'll be going to write this one-liner, but let me explain this one by one, what is happening. Now, this is basically the difference of every data point, the difference of every data point just. So 120 data points from 30 data points, and the difference of 120 from 30. And the difference is again point wise, element wise. So this basically, these commands, they are doing broadcasting for me. Next, what I do basically is I do the square distances. So what I do really is I just take the square of all these elements. So what will happen is, again, after this command, I'll be having the square distances now. What next I do is I just basically squeeze this dimension, because that is something that I don't want for Euclidean distance. And what I do is I set the axis equals to 2. And what will happen is these square differences, they will add up, and I'll be having a complete distance matrix which has shape 120 by 30, which means if you just see that what's the d of what's the d 0, 0, that is basically the distance of the first training sample from the first test sample. So what is the d, for example, 0, 15? That is basically the Euclidean distance between the first training example from the 16th testing example. So this basically, this D matrix, D, it contains each and everything, all the distance measures from the training samples to test samples. And see, we have just written one line of code in NumPy, and everything is achieved completely. Great. What next? Next, what we do really is we basically try to build the nearest neighbors. So let's sort the arguments. Let's sort all these distances and find out the indices where they are sorted in column order. So let's see, for example, the nearest index. The nearest index is np.argsort. So give me the arguments, the D matrix, and the axis is 1. Wow. So that NIDX, if I just show you that, that says, okay, for example, if I just print NIDX, let me just print the row 1 of it. Let me just print the first row, and just let's say we have 5 neighbors. So what is happening? Why this NIDX is what kind of array? Am I missing something? What is the shape of NIDX? NIDX dot shape. That's this 120 by 30, makes sense. So now NIDX, I go inside and I print. Oh, I have to print the 0. That's the first row, and then I print just the 5 neighbors. So this will give me the first 5 neighbors of the training sample. So the first training example has these 5 neighbors. Basically, the first training example have these 5 neighbors. Or what are the first 5 neighbors of the first testing example? So let's say n idx and n idx. Let's say we pick first 5 for the first testing example. So these are the 5 neighbors. Training example number 27, training example number 28, training example number 8, training example number 5, training example number 0, training example number 17. These are the 5 top neighbors of the first testing example. So for example, if I want to classify my first testing example based on the 5 nearest neighbors, or maybe the 10 nearest neighbors. So let me try to classify the first testing example based on the 10 nearest neighbors. What are the 10 nearest neighbors of the first training example? So they are 27, 8, 5, 0, 17, and all these ones. Okay. So what I really do is I make that as an index. So what I next do is I see in my training example, why train, what kind of class actually wins. Oh, what's the problem? Object is not callable. Why not? Why train is not callable? Oh, again, my bad. So here you can see class 0, class 0, class 0, class 0, class 2, 2, 2, and then class 1, 1, 1. Basically, which one is occurring the most? Maybe we can call a mode function, np dot mode. Maybe the np dot mode is available. Let's see. Hope it is available. That is the statistical mode, and see which class basically wins. Oh, np.mode is not available, has no attribute mode. How can we check the frequency of, yeah, np.mode is not available. That's bad news. How can we check the frequency of the most occurring element? Which element occurs the most? Well, we can write our own function for that, but there should be an np.mode. Let me, for example, let's see where is. So this is maybe we should write our own function, or maybe we should consult maybe SciPy. Why not? So there's a stats module in SciPy. So let's just bring that SciPy, import stats, and then just compute the stat mode. Why not? So rather than using np mode, let's use this stats dot mode, and it should give the result. Yeah. So the mode is basically 0. So the class 0 wins for the very first point. So what if we want to compute the top 10 nearest neighbors? Basically, we already have done the arg sort for training. Maybe we should do the arg sort in axis 0, because we are going to compare these test examples with respect to we are going to find out the neighbors for test examples that appear in row form rather than a column form. So if we do that, for example, the result may just change, and the statistical mode again is 0 in this particular case, and the count is 10. Oh, the count is 10 basically. So we were just doing this wrong. The axis should be dealt with 0 rather than 1. So so the element number 0 is classified as to be in class 0 by our method. Let's check the exact label of that. What is the exact label of this element at 0? The exact label is also 0, so we have classified well. So we can classify, for example, what if we want to classify our the element number 16, which is indexed as 15. What is that? So let's see that. That is again classified as 0. Let's check what is there at, that is also 0. So yeah, I mean, in y-test, however, there are a lot of there are different labels. So right now, using this k nearest neighbor that we have just written, we are able to classify each and everything just very quickly. The purpose here is to not basically teach you or tell you what a k nearest neighbor is. The purpose here is to just tell you the power of NumPy, how quickly we were able to compute this distance matrix, and how carefully we apply this argsort function just to come up with the decisions that we really want to make. And a similar kind of implementation is available in the built-in scikit-learn package. Further, we saw this train test split, how carefully we use this random package and the random permutation to just do the indexing and make a random split to whatever size we want. A similar kind of function is available in scikit-learn as a built-in function. So yeah, that's with these examples, I stop here with these examples, and I hope that your knowledge and grip on NumPy, particularly indexing, should be indexing and universal function and use of those. It should become very powerful then as compared to earlier. So in the next video, we'll be talking about the structured array. That will be the last video in this NumPy package. And after discussing the structured array, we will be silently moving towards the pandas library or pandas package that builds on top of NumPy for data manipulation. It gives much more power than NumPy, although it builds on NumPy. So hope to see you in the next video with structured array. Okay, in the last video, we talked about k nearest neighbor. We built k nearest neighbor from scratch in NumPy. In this particular video, that's basically, I'm planning this video to be the last video for NumPy for this course. I'll be introducing how NumPy can be used for heterogeneous kind of data. You know that NumPy basically handles the same data type kind of elements for all kind of efficiencies and all kind of speed ups that NumPy really guarantees. But there is a way to actually store heterogeneous kind of data, the data that involves, for example, integers, strings, and floating point numbers, and another data type, data that is mix of several data types. There is a way to manipulate that data using NumPy, and that kind of data sometimes called structured data or records that usually make the basis of databases. And the introduction to structured arrays using NumPy will give you a very good look and feel how basically pandas is built on top of NumPy. So the example that I'm going to show you just now will give you a look and feel, and you'll get convinced that yes, pandas, how actually pandas built on top of NumPy, and how actually all the efficiencies that NumPy offer, pandas actually use that those actually enjoy all those kind of efficiencies inside. So let's go to our friend Jupyter Notebook just to see how these NumPy arrays, they can be used to store structured data or the data that occurs in records form or that may have mixed kind of types and stuff like so. So yeah, let's go there. Remember, I have just I can change the view of this Python whenever you want, this IDE whenever you want, just to make this writable area larger. I'm just hiding these kind of bars that are available. Okay, so let's say we have x equals NumPy array. Let's build an array with, let's say we have an array with let's say a name. Let's say this is an array that stores different records, and the first record and the record has, let's say, 4 fields. Let's say the field is let me describe all the fields here. First, the fields is, let's say, D type. The fields are, let's say, the first field is, let's say, the name field, name of a student. Let's say that's a student record. and the name of the student has type, let's say, Unicode string with maximum characters 20, let's say. Then we have another field, let's say the student ID. Let me call that ID of the student, and let me write this name as name with capital N. This ID, student ID, that again, let's say, is a Unicode string with the maximum, let's say, 10 characters. Then we have, let's say, the marks of the students. Let's say a particular student has some marks. Let's say that's a student database. We are building a student database, so marks. And let's say the marks has data type. Let's say, let me shift that to another line. Let's say the marks has data type integer 8. Let's say that's integer 8. Integer 8 bytes integer. And then we have another field in the record. Let's say that is the GPA of the student, or CGPA of the student, or grades of the student. And let's say that is floating point with 4 bytes. These are, let's say, a record contains name field, which is a string type, ID, which is a string type, marks, which is an integer type, GPA, which is a floating point type. And let's say this is here is the data that we are supplying. Let's give 2 records. Let's say name is ABC1. That's the name. The ID is data understanding and visualization 001. That's the ID of the student. Let's say, and the marks. Let's say the marks are 90. And the GPA is, let's say, 3.78. That's the GPA. That's our first record. Let's give a second record as well. The second record is basically this. Let me just switch that second record on to the next line. The second record, the name is, let's say, 2. This is 2. Let's say the marks are, let's say, 70, and the GPA is, let's say, 2.81. Let's say if we just build that array, then now if you, for example, want to access all the values, all the names, what are the names of the students, if you want to access those, all the names, then all the names are ABC1 and ABC2. If you, for example, want to access the name field, if you want to access the name field as well as the GPA field, if you want to access these two things together, you can have this. So for example, that's the name and that's the GPA, that's the name and that's the GPA. So that's what is returned. So now you can index the array using the string, using the names of the records that you just saw. You can index multiple columns if you want, and all that stuff. Basically, this is the view of this kind of structured array is actually the basic building block of the library pandas. You should be, if you're comfortable with this, you will be much more comfortable in pandas, because that should give you a look and feel how pandas basically work. Pandas basically deal with this structure kind of data where we have a lot of records. Each record is just a column. Each column has a name, a column name, and we can access the values. We can manipulate the values. We can play with the values just using I mean, there are several ways of indexing, just by indexing by just name, or indexing by integer numbers and all that stuff. Further, I want to mention that although although you work with the structure kind of arrays, if you see in the NumPy array, each array basically has this structure. So that's one element in the array. That's the second element in the array. And if you see the basic theme of NumPy array, each element of the array has same kind of data type. Here we say each element of the NumPy array has same kind of structure, or whatever the mixed data type is, that stays same over the records or over the elements. And that again gives the same kind of efficiencies that you have observed in the NumPy arrays working on just integers or floating point numbers or just strings. The same kind of efficiencies are there. And these efficiencies are, one of the way that pandas becomes much more powerful and popular. Not just efficiencies, apart from efficiencies, the way pandas basically deal with the data and the high level interface that actually supply a lot of functionality to deal with data that actually brings the popularity of pandas much more as compared to other packages. So I end NumPy here, and in the next video we are going towards pandas. That's a data science package, very, very powerful package that builds on top of NumPy. So hope to see you in the next video.
So we're learning structured array. We in lecture 34 we've learned structured array. So let's make one. Our task is to make a structured array with 4 fields. The fields are employee type, which is a string. It should be permanent or non-permanent. The input should be permanent or non-permanent, right? Then the second field should be age, which should be an integer. Then there's birth year, which is again a string, only the year of the birth, right? Then there's salary, which is also integer. So we have to make 3 entries for the structured array. So we need to make 3 entries and then show each field. Each field means for every entry we need to show employee type and then age and the birth year and then the salary, right? So we need to show these individually. So it's pretty easy. Yeah, it's easy to code. So I'll code it for you guys in the next video. I'll see you guys then. Here is the quiz for lecture 34. Let's solve it together. So we have to make a structured array with 4 fields as I described before in the last video. So let's make this structured array. Let's say the structured array is, let's say it's x. X equals to np dot array, right? And the syntax for it is, let's first write the data types. The d type equals, oops, right. So first field is employee type, right? And it was supposed to be a string, so I'm just gonna write here u20. Yeah, that should be enough. So next we have, I think it was age, right? So age should be integer. Yeah. So I8. Then there was, oops, birth year, which was also a string. So let's say u10. Then the last one was, I think salary, and salary was also an integer. So let's say I8. Okay, these are the fields, and now let's make the entries. We had to make 3 entries. So let's go on with the first entry. And just want to make sure I don't make any syntax mistakes. Yeah, so here we'll have the first entry, and let's second. Okay, so let's say first employee is permanent, and his age is 31, and the birth year is 1990, and let's say salary is 50,000. Okay, so next employee is, let's say now he's non-permanent, and age, let's say 24, then let's say 1997, and let's say the salary is 25,000. Okay, then we have the third entry, that is, let's say, permanent again, and age is let's say 36, let's say, and the birth year is 1985. Oh, this was a string. Okay, so this was a string, so yeah, 1985, and let's say the salary is let's say 50,000. Oh, not 5 lakh. Let's say 50,000. Okay. Right. So, right, there should be a comma here before specifying the data type. So let me run this, and I hope there are no syntax mistakes because, and there's a syntax mistake. And what does it say? Okay, brackets. Oh, I missed these brackets, I guess. Let's hope that's the issue. Yeah, that was the issue. Okay, so now our next task was to show each field, right? So showing each field means X. I want, let's say, I want the age, right? That's what I want. Okay, so 31, 24, and 36. Perfect. Then I want the field that is employee type. Permanent, non-permanent, and permanent. Okay. So it fetches each field of the entries and it displays them. Then there's, let's say, salary. Perfect. And the last one is birth year. Oops. Had the caps lock on. Birth year. Great. Okay. Simple enough. And yeah, this is also pretty cool. It's a pretty cool way to sort of organize your data. Okay. So that's all for this quiz. I'll see you guys next time. Goodbye.